In this video, we're going to talk about equilibria in solutions that contain weak acids. So for example, if we have a weak acid, and we're just going to use a generic acid that we call HA, if we have that in solution, we have an equilibrium going where we're going to have a certain percentage of the weak acid that is not dissociated. So we're still going to have some HA molecules floating around. But some of those HA molecules are going to break apart and form hydronium ions and the anion. So we can write an equilibrium constant expression for this equation. And remember, we don't include liquids in the equilibrium constant expression. So if we wrote the equilibrium constant for this equation, it would be, both of our products are aqueous, so they would be included, and our acid is aqueous, so it would be included, but we don't include water since it's a liquid. The equilibrium constant, when it's written for an acid, is actually given a specific designation. We call that Ka. So Ka refers specifically to the acid dissociation constant, and you will see the format is exactly the same as what we wrote for the equilibrium constant. So Ka is equal to H0 plus times our anion over our acid concentration. So we're going to look at some calculations where we have to use this equilibrium constant expression. So let's look at an example here. We have the pH of a 0.250 molar hydrofluoric acid solution is 2.036. What are the values of Ka and pKa for hydrofluoric acid? So let's start by writing our Ka expression. So if we write the Ka expression for hydrofluoric acid, so we would have H3O plus times F negative over HF. Now we want to know the equilibrium. We want to know Ka and pKa, which means that we need to know the concentrations of each of these species at equilibrium. So we're going to make an ice table, just like we did in an earlier chapter. And let's get rid of this extra line here. So we have hydrofluoric acid, and then we have H3O plus and F negative. So initially, we start with a concentration of 0.250 hydrofluoric acid. And at the very beginning, when we first put this in water, at the instance that we add the hydrofluoric acid to water, there is no H0 plus or F negative yet. Over time, some of the hydrofluoric acid is going to break down and form hydronium ions and fluorine ions. So we're going to see the appearance of some H3O plus and F negative. So at equilibrium, our concentration of hydrofluoric acid is going to be 0.250 minus X, and our concentration of H0 plus and F negative is going to be X. Now we have something else here that will help us out. We have the pH. So let's go ahead and plug in our concentrations of H3O plus, F negative, and HF into our Ka expression. So we have Ka is equal to H3O plus times F negative over hydrofluoric acid. And according to our ice table, our concentrations of H3O plus and F negative are X, and our HF is 0.250 minus X. Now we have the pH here, which will help us because pH is the negative log of the H3O plus concentration. So if we want the H3O plus concentration, then what we can do is take the inverse of the log. So we would have H3O plus is equal to 10 to the negative pH, which is 10 to the negative 0.250. And if you plug that into your calculator, you should come up with 0.00920. And this is the concentration, so it's in units of molarity. Now that we know what H3O plus is, if H3O plus is X and F negative is X, that means the concentrations of these two are equal. So we can plug this in for X. So we would have Ka is equal to 0.00920 times 0.00920 over 0.250 minus 0. And if we multiply this out, that comes out to 3.52 times 10 to the negative 4. So this is our value for Ka. The question also asks us for the pKa. So pKa, just like pH is the negative log of H3O plus, pKa is the negative log of Ka. So it's the negative log of 3.52 times 10 to the negative 4. If you plug that into your calculator, the negative log of 3.52 times 10 to the negative 4 comes out to 3.45. Okay, let's look at another example where we're dealing with an equilibrium of a weak acid. So the question asks us to calculate the pH of a 0.10 molar HCN solution. At 25 degrees Celsius, Ka is equal to 1.4 times 10 to the negative 9. Now, if this were a strong acid, since there's only one hydrogen and one proton in our acid, then the molarity of the acid would be equal to the molarity of the H3O plus. But this isn't a strong acid. When this dissociates in solution, we're still going to have some HCN molecules floating around, along with some H3O plus and some CN negative. So we don't know from the concentration of HCN what the concentration of H3O plus is. So we have to do some calculations here and figure out what our concentration of H3O plus is. So let's start by writing the expression for Ka. So Ka is going to be equal to H3O plus times Cn negative over HCN. And we're going to make an ice table because we're going to have to calculate the concentration of H3O plus. So we know at the start, when we make this solution, the concentration of HCN is 0.10. And at the very beginning, the concentration of H3O plus and Cn negative is going to be 0. As this HCN is put in solution, some of it is going to break down into H plus ions, which are going to react with the water molecules and form H3O plus. And we're also going to get some Cn negative ions out. So at equilibrium, the concentration of HCN is 0.10 minus X, and the concentration of H3O plus and Cn negative is X. Now this time we're given the Ka and we're trying to calculate pH. So we have to calculate what the concentration of H3O plus is. So we're going to plug in what we know. We know that Ka is 1.4 times 10 to the negative 9th. We know that we can represent H3O plus as X and Cn negative as X. And we can represent HCN as 0.10 minus X. Now, if you try to work with this equation as it is written, what's going to happen is you're going to end up with X in multiple places. X times X on the top is X squared, but then we have an X on the bottom. And that poses a little bit of a challenge algebraically. What you're going to end up with is what's called a quadratic equation. Now, sometimes you have no choice but to deal with a quadratic equation, and we will talk about in class how you deal with those situations. But for now, we're going to take a shortcut, and we're going to assume that the value of X is so small that we can assume that it's negligible. So we're going to ignore this X here and say that it's so small that we can essentially consider it to be 0. Now, this estimation only works in certain cases, and we'll go into more detail in class about when you can use this approximation and when you cannot, and what to do when you cannot do it. But for this problem here, we're going to go ahead and use the approximation so that we can calculate the pH of the solution. So we would have 1.4, not 1.49. So 1.4 times 10 to the negative 9th. On the top of this equation, X times X is X squared. And we can simplify the bottom of the equation to 0.10. So now I can multiply both sides by 0.10 so that I get X by itself, or X squared by itself rather. So 1.4 times 10 to the negative 9 times 0.10. If you put that into your calculator, you get 1.4 times 10 to the negative 10 equals X squared. If we take the square root of that, we get x is equal to 1.22 times 10 to the negative fifth. Now, technically, when you take a square root of something, you get a positive and a negative result. But the negative result doesn't really matter here, because you can't have a negative concentration. That's not physically possible. So we just ignore the negative and only take the positive square root. So, actually, let's take a step back here before we get to pH. We labeled the H0 plus concentration as X. So this is also the concentration of H0 plus. Okay, it's also the concentration of CN negative. And we could go back and calculate the concentration of HCN by taking 0.10 minus this value. However, let's look back at the question. The question only asked us to calculate pH. And to calculate pH, pH is equal to the negative log of H3O plus. So the only thing that we actually care about is the H3O plus. So when you're doing these types of problems that have multiple steps, sometimes there are a lot of things that you could calculate. So be careful as you're going through the steps that you don't get sidetracked. And remember what it is that you're actually looking to calculate. Okay, you can go calculate everything else if you want to, but you're just doing extra work. You're not really going to be getting yourself anywhere if you're calculating things that the problem didn't ask for. So those are all nice things to know in some circumstances, but what we want to know is the pH. So all we need to figure out from the information we have down here is the H0 plus concentration. Since H0 plus we represent as X, we already have the H0 plus concentration. So now we can take the pH is equal to the negative log of H0 plus, which is 1.22 times 10 to the negative fifth. And if you put that into your calculator, you get a pH of 4.91. So this is the pH of our solution. If you took the negative log of 0.10, you would not get 4.91. You would get a much lower number. That's because HCN doesn't dissociate completely. So the concentration of HCl plus is not 0.10, but it's actually 1.22 times 10 to the negative fifth. So this gets you the pH of your solution. So we're actually going to stop here, and we will get some more practice calculating pHs and weak acid solutions in class. So I will see you in class.